Hello, my name is Konstantin Burlachenko. I'm a PhD student and member of Professor E33 Optimization and Machine Learning Lab at Chaos. In this presentation, I will present MARINA. This is our joint work with Edward Gorbunov, Giseli, and Peter Richtari. To motivate you to watch this video to the end, I can say in advance that all our methods presented in the paper are superior to previous state-of-art methods in terms of the oracle and communication complexity in the class of non-convex distributed learning with compressors to today. If I have motivated you enough, then let's go to the problem definition. We minimize function fx, which has the finite sum structure, and optimization variable is x. It belongs to the space Rd, where d is number of simple scalar optimization variables, n is number of workers, and fi is a local loss on the data accessible by worker I, or it's just some optimization function available to the worker I. Fi has the structure that can have the structure that it is finite sum, or it can be infinite sum, but it should has the form of expectation. Because optimization function is f is a sum, it can be easily observed that we cannot really, without extra assumption, solve this problem in a completely decoupled way. So some communication between FIs are needed, between workers are needed. And typically in this optimization, people exploit such star-based topology. In such setting and another settings, the communication is typically a bottleneck. So this bottleneck should be addressed and handled. So how people handle this? There are three main approaches. They change the topology of the network. They do more work on each worker and they hope that communication less. It will bring to the situation. Or they send less information between worker and server to reduce the communication cost. MARINA uses the last approach and has built-in support for an unbiased compressor. Unbiased compressor is a randomized mapping from X to QX such that it is unbiased and its variance is bounded below by quadratic form with this multiple factor W. There are a lot of compressor operators, but maybe it's a more nice example from the class is RANDK. It works the following way, so it's pretty simple. It takes as input vector from RD, and then it selects uniformly at random k components, make them non-zeros, and another d minus k components are zero out. With appropriate scaling, it can be shown that this compressor is unbiased, and it has this W constant. To use MARINA for specific algorithm, your function f, which you minimize, should satisfy two properties. It should be bounded below by f star, and also functions fi can be non-convex, but its Lipschitz gradient should be L smooth. And MARINA, as a final goal, solve the following optimization problem. It's find x hat such that an expectation, the norm of the gradient will be less than epsilon squared. It can be easily shown that from this inequality, the following inequality holds. Expectation of the norm of the gradient less than epsilon. So we find epsilon stationary point. In the paper, we compare with previous state-of-art algorithms, but for purpose of this presentation, I mentioned only one Diana. So in Diana, the number of communication rounds depend on this factor, and MARINA have improved this factor by number square root of W. It has the same dependency on epsilon, which is a relative, which is epsilon from this requirement. In the paper, we have presented different variations of MARINA, which is working with batched data, and MARINA, which is working with partial anticipation. For purpose of the experiments, we consider LibSWM dataset and fit linear models, but with a non-convex loss in the following form. Also, recently we have carried experiments with training ResNet 18 at CFR 100 and compare VR MARINA, VR Diana, and VR MARINA with non-compressors. So we have observed that compression is really a help for this particular example. So we think this is a great method and hope for future development. Thank you.